My talk is based on a joint work with Paweł and Michał Lipiński, and it is motivated by analysis of time series, but inspired by some methods from dynamical systems. So I'm happy that Niklas already mentioned this Taken's embedding theorem, because it was, let's say, sort of a starting point for us. So, namely, as we can imagine, it may happen that there is some system which might be a biological, physical system that is very complicated, highly nonlinear, highly dimensional. And we have very limited information about the system because we only take some low-dimensional measurements at some consecutive time instances. Yes, so such a function that we measure is called observable, and the challenge is to try to deduce some information about the whole system from these low-dimensional measurements. And this was somehow captured. This is somehow captured by the notion of embedding, and I think I will not maybe discuss this mathematical definition, but instead I will go to another example. So the example that we are all familiar with is the Lorentz system, which is it's three-dimensional, continuous dynamical systems, and for some choice of parameters, it produces this well-known Lorentz attractor in the shape of butterfly. And we can produce, yes, a time series. I mean, we sample the trajectory of this time series, yes, at some time steps, yes. So we take some time, t till gamma, and so on. So if we, trace the trajectory, I mean, all the coordinates, x, y, z, and we plot them, we obtain this Lorentz attractor, yes. But imagine that maybe because of some reason you only see the values of x coordinate, yes. So you have a one-dimensional time series, a time series that consists of consecutive values of x measurements. Yes, so there is a x1 measured at time t1, x2 measured at time t2, and so on and so on. And if you do a three-dimensional embedding, that is, you take this time delay vectors or this sliding window embedding. So your first point is x1, x2, x3, then the next point, let's say, the graph one will be x2, x3, x4, and so on. And if you plot these three-dimensional vectors that are just obtained from values of x coordinate, you'll get such a picture. Yes, so that looks similar. And there's Taken's theorem, and originally formulated in, I think, 1981, and then there are some other versions of it which can actually explain why this is not so surprising. Of course, you need some assumptions, so it's like Niklas mentioned, except for some regularity of the signal and observable. One of the important assumption is that how long, what is the embedding dimensions of how long are my delay vectors? Yes, so here we took 23D, and originally Taken's theorem, we need to take the dimension which is greater than 2 times the dimension of the manifold, or if the omega limit set of the trajectory is in attractor, then let's say 2 times and some fractal dimension of box dimension of this attractor, or house of dimension, depending which version of Lacan's theorem you use. Yes, and another assumption, just for curiosity, is this choice of the option variable. So, because, for example, if you only take look at z coordinate, then you actually here you want to like I'll say recover the whole attractor. You will see, like, let's say, like one wing of the butterfly. Yes. So here, for example, the z observable is not generic. This is in terms of Lacan's theorem. Okay, I keep the details here because what actually Lacan's theorem says, so what it means to reconstruct the system, to reconstruct the dynamics, because it's not only to obtain a similar picture. Yes, it's about also having some sort of dynamics on the system that is obtained by delay vectors. Yes, but our delay vectors, they're obtained from a time series. Okay, but maybe so what Paredes and Bacon theorem actually says that that you can reconstruct the dynamics on this system created from this delay vectors. Yes, because as I said, they are sort of ordered, so we can have a dynamics which is like a shift map on this vectors. Yes, there's a trajectory. Yes, we know which part is first, which is the second, and so on. Embedding, and the conjugating map is actually the map that is the embedding. Mathematically, the concept of two systems being, let's say, equivalent is captured by notions of conjugacy. So in dynamical system, we say that two systems are topologically conjugate. Yes, so we have two systems F and G. Yes, discrete dynamical systems. They act in some topological spaces X and Y. And if they are conjugated, there exists, a homomorphism from X to Y, such that this course of the following diagram completes, so that it is equivalent to choose a point in X, map it to F, and then apply H and arrive at some point at Y space. This is the same as if we took this point first in X, then map it via H to Y, and then apply GS. So if such a map exists, if this is a homomorphism, then the systems are topologically conjugated. If it is not a homomorphism, but continuous surjection, then we say that systems are semi-conjugate. And actually, this Lacan's theorem allows us that conclude, yes, that this, when we have the system, when we have the trajectory in this space of embedding vectors, and if you apply the sort of treatment, then it is like a conjugacy, yes, or sometimes you obtain sometimes this map H is actually not a conjugacy but an injective function, but it's still a very important, still good. Okay, I mentioned this dimension of the embedding, and of course this is something that we do not know a priori, yes, because if we don't see our system, like, okay, for Lorentz attractor, it is known the dimension, yes, of the attractor is more or less estimated, yes, but usually we don't know. So of course the question is, if you just have a time series, then what embedding dimensions so be in my case, and perhaps also which lag L I should choose. And there has been many heuristic methods proposed so far. And one, I think, of the most recognized classical methods is the method called false nearest neighbors. So it is based on observation that if you do a d-dimensional reconstruction and you just you pick a point in this d-dimensional space, you look for its nearest neighbor, and then you look what will happen with this pair of two points after some very small step ahead. And if these points, being originally nearest neighbors, if they deviate too far, then you say, okay, they are probably not nearest neighbors, they are so-called false nearest neighbors, because if we assume yes that we are in the deterministic setting that of course we do here, then even if our system is chaotic, it is still the iterates of some continuous map, and two points that are very, very close, they cannot go arbitrarily far. Yes, let's say it is like maybe if you consider, for example, a point, I don't know, 2 points in 4-dimensional space, then they may be very close. Maybe they are even at the same point. But if you add another coordinate, fifth coordinate, yes, so you just increase the embedded dimension. Then you see what will be the nearest future evolution of these 2 points. Yes, so this is the formula for the false nearest neighbor statistics. So we just say choose dimension d, for each point compute its nearest neighbor. Yes, so this is the point. Calculate this distance and then take these 2 pair of points, add another coordinate and check if their distance has increased more than 4 times. Yes, where 4 is of course parameter of the method. We do this for every point. Here, this is some term to discard the outliers and the points which are far away and it does not make sense to consider them as neighbors. This is a sort of normalization term. And you calculate the statistics for different values of areas, you obtain a sort of curves, and for each dimension, you compute this curves. If you notice that for some d, it goes decays fast with R, then it says, okay, this d is probably right in the dimension, yes, or reasonably close. So we decided our first approach was to look at this method as the method of measuring of, let's say, similarity or a conjugacy between 2-time series. Yes, because if we are in the right embedding dimension, then it means that we have, let's say, reconstructed the dynamics. So the trajectory in d-dimensional setting should correspond to the proper trajectory in d+1-dimensional settings. Yes? So this statistics, as you saw, should be low. Yes. So okay, we can just say that we want that we have 2 time series, let's say A and B. So there might be trajectories of dynamical systems or just trajectories of embedded time series. And then we do the same. Yes, so we choose a point in this first trajectory A. We look at its nearest neighbor in time series A. We need to pick some corresponding point in the other time series. So if we assume that A1 corresponds to that AI corresponds to BI, so that there's a time shift then. we find a point VI, and we check, and then we take the correspondence of this point in the other time series, yes, and we have the time series, and we compute this. So for example, if AJ was the nearest neighbor of AI, then it means that here I have great distance of BI and BJ. Yes, let's say, assuming that this is correspondence between the two time series. And in this way, it checks whether trajectory BI corresponds in a way to this trajectory point AI. Okay, but then we had the idea why not to look at a big, greater, discrete neighborhood. So maybe instead of considering the nearest neighbor, let's consider k nearest neighbor, so that we take into account also a sort of, let's say, a topology of the neighborhood of the point. So imagine that this is our first trajectory, our reference trajectory A. And this is the other trajectory we want to somehow compare A versus B, yes? So let's pick a point, for example, A6 on this trajectory, and let's say that K equals 4, so we look at the 4 nearest neighbors of A6. So, okay, taking this equivalent distance, but maybe you can try some other distance as well. We see that we have A3, A4, A9, and A8, yes? Okay, so if we want to check whether there's like one-to-one correspondence between the points in time series, then this gives me A6 is sent to B6. Yes, then A3 goes to B3, A4 to B4, and so on. But it looks like, you know, in order to include in the neighborhood of point B6 correspondence of these points that were present in this orange neighborhood, it ends up that there are actually some other points which are even closer to B6. Yes, so B5 and B7. So that is a sort of measure of the difference between neighborhood of a point A6 and its corresponding point B6 on another trajectory. Yes, so that's let's say a discrete measure. I had 6 points, but here just 4. So the difference is 2, and this is what goes to the numerator in this formula. Yes, we do it for every point. There's a sort of normalization, and we obtain a sort of measure of similarity, discrete similarity of trajectory A versus B. Yes, and as we expect, when it happens, is that the low value, I mean, this can be justified. The low value of this quantity TNA-AB indicates that B is this semi-conjugate to A, and I mean, indicates if you are semi-conjugate, then you should expect this value to be low. If you have a conjugacy, then both of these quantities, because they may not be symmetrical, should be small. So we have thought also about another measure which would be directly, let's say, inspired by this commutative diagram. I showed on, I know, the second slide probably. So if you fast here. Yes, if you remember here, yes, we can again imagine that we travel this diagram both ways, and we check what actually we obtain. What is the difference between what we obtain in traveling this in one direction and in the other? Yes. So. So it is that if we choose some neighborhood, let's say we choose K, nearest neighbor of the point AI in reference time series A, we sort of map it to FT. I mean, even if we don't know F, because we usually don't have any formula for F, then we can, it means that we just look at points in this time series which are T time steps in the future. Yes, P is the parameter of the method. This is a time series, so we know what point is going. We map it to H. H is some sort of choice that we need to make. Again, we don't exact formula for H, but never mind, we should decide about some mapping between the indexes of one time series and the other that we would like to test, in this method. The first choice, you can always try, identity matching. And what we do on this, let's say, corresponding space, yes, we choose corresponding points in the second time series, and we map it by T times. We look at points which are T times steps ahead in the second time series. So, okay, let's maybe have a look here. So let's choose K equals 2. I have a point AI. I choose 2 nearest neighbors of AI, so I have this blue point cloud. And okay, somebody gives me some formula for A, yes. So let's imagine we compute for AI, yes. I mean, for a moment, let's imagine it. Of course, it may happen that such a point is not, usually it is not in this corresponding time series B. So we find a point which is the closest, we know the H tilde of AI. And then we look at 2 nearest neighbors of this point in this B time series. Yes, so, no, sorry. Then we apply H to these 2 points again. Yes, so of course we obtain some, we denote them H because again we may not exist in these time. But again, so if we consider only, let me go here. Yes, sorry. But so then we have like this blue cloud in the second time series, and we denote H of U. And again, it may happen that some point in this B time series are actually closer to this, theoretical point HI. So if we want to include it, we have this enriched red neighborhood, which we denote with the plus index here. Yes, and then depending whether you put this smaller blue neighborhood here or this larger red neighborhood here, we have these 2 formulas, yes, for conjugacy test and conjugacy test plus how we call them. Yes? So what we do, we look at this blue point cloud. We map it T times ahead. Then we apply H, yes, or for the indexes, and we have some point cloud. We do the same with either blue or red point cloud here. I mean, the same. The difference is that we look at the time series B. Yes, of course. So we look at the evolution T times step ahead of, for example, this blue point cloud. We check that the Institute is different than what we obtained here. So we can then compute how's the distance between these 2 points clouds, and we do it for every point. We have sort of normalization of these 2 formulas. So, as I really do not have much time, let me just mention that we group sort of convergence results for this test. I mean, if you are conjugate or semi-conjugate, then under not so strict assumptions, you obtain low values of this test. That is that. Yes, so small values of this test should be made like a hint that okay, there is a chance that you are really conjugate or semi-conjugate. However, if you obtain large values of this test, then it means that our time series will differ significantly in a quantitative way. So we performed a couple of experiments. First, it was the toy example, with a logic and the tent map, because here, as we probably all computed at some point of our university education from this conjugacy map. So this is a clear test, and we computed a reference time series. So we pick a point, we see a logistic map with parameter 4, trajectory, and then we took a corresponding point in this end map. So of course there should be no large conjugate. Yes, there are corresponding trajectories of conjugated system, and this was captured by all these 4 tests. Yes, then we consider a perturbation of either starting point, parameter, or both. Yes, and here, for example, this FNN and TNN, the values increased fast, so that gives you a sort of binary answers. Yes, we also increased. We also showed that these values increased. But here, it was really, let's say, more continuously dependent variation of starting point of system parameter, which might be good if you have actually sort of real data, yes, because mathematically, okay, these trajectories are no longer conjugated. However, numerically, that's close, which is captured by our test. Okay, I will skip it because I'm really almost at the end of my time. So a couple of more experiments. We have also one of our last experiment was let's say that consider neuronal pipelines. However, it was also obtained by some model, but the model was actually got it from a group of people at the Nancy, and based on the behavior of some neurons and some crab living in Boston or I don't remember exactly. But never mind, this is a special transcript, because if we want to test whether a model can reproduce a sort of real data, then always at some point we need some measure, like to say you are already close to your goal, or no, you are what the model produces far from what you want to achieve. So we need a sort of measure, score. And here the baseline was this orange time series, and we also had a couple of blue time series which were produced by the model. And here it nicely what's interesting in this prototype series that we have both slope oscillations, yes, and this spikes that are grouped into bursts. So you have like 2 time scales, yes, and we think that this method actually performed well here, but I don't have much time to discuss it, so I will stop here. Again, yes, the software is in GitHub, the details are submitted and also available on archives. So thank you.